In class, somebody tested their reflexes, and what happened was somebody was holding the ruler here, don't make fun of my art, and they dropped it, and this person here grabbed it as soon as they could after the ruler was dropped. And if I remember correctly, the ruler dropped all the way to 22 centimeters before she caught it. So this is what it looked like when she caught it. What we want to figure out is how long it took her to actually grab it after it was dropped, which would be the reaction time. So we can identify the variable we want to solve here, which is t, or delta t. So our job is to find an equation to use that will allow us to solve for delta t. So let's think about position and displacement. Our rulers basically are coordinate systems. So if we started on 0 centimeters on the ruler, that would be our initial position, and then the final position would have been the 22 centimeters. We know the velocity was 0 initially because it was a stationary ruler, and nobody knows the final velocity. We didn't have a radar gun or anything. What about acceleration? We do know acceleration. We know, because this is on the surface of the Earth where this event is occurring, we know that neglecting air resistance, an object in free fall must be accelerating downwards at 9.8 meters per second squared. And here's an advanced note, an advanced concept. We know that the 9.8 meters per second is occurring downwards. So if we're going to let this be a positive 9.8 meters per second and not make it negative, we have to decide that downwards is our positive direction. And since the ruler is being displaced, its direction is shifting in the downwards direction, we can also call this number positive. And we don't have to make it negative 22 centimeters. So here's the hard part, finding out what we're going to do with these variables and numbers. What equation are we going to use? So take a minute, see if you can figure out what equation would be the best to use here. Only one of these 4 equations doesn't have final velocity as one of the variables in it. It's the very first one. And here's something handy we can do. We know that VO equals 0, so regardless of what time is passing here, regardless of what t is, this VO times t is going to be 0, because 0 times anything is 0. So we can basically just eliminate that there. And we also defined our initial point as being at point 0 on the point 0 position on our coordinate system. So we can just eliminate that guy. And that leaves us with a much simpler equation that you often see. And you can write it this way: if your initial position is 0 and your initial velocity is 0. And now it becomes much more manageable of a job to solve for t. So I'm going to try to isolate t here. I'm going to move a from the top on the right to the bottom on the left. And to get rid of that half, I'm going to multiply both sides by 2. I'm going to continue working up here. We're almost there. We've isolated t, but it's t squared. We don't want t squared, we want just t. So what we really want is the square root of t squared. So if we take the square root of the right side, we just take the square root of the left side. So what we're left with is t equals the square root of 2x over a. And we've solved for our unknown variable that we were curious about, and we can just put in the numbers. Or can we? Let's see what happens if we put in 22 centimeters for x, and we put in 9.8 meters per second squared for our a. Let's think about how would our final answer look in terms of the units. What would be the units of our final answer? Well, we would have to take centimeters and divide by meters per second squared, and we would have the square root of all that because it's square rooted. That is a huge mess. That is a big problem. That is not working. So we see that in order to cancel meters, we need to make meters go away because we want to just leave seconds because we're solving for time. So in order to make meters go away, we have to make the units consistent. We have to convert centimeters to meters. It's sometimes just safer to use always SI units, although you don't always have to. But let's convert that 22 centimeters to meters. Here's our conversion factor. We know we want to put centimeters on the bottom so it'll cancel. We're relating centimeters and meters. We know there's 100 centimeters in 1 meter. 22 divided by 100 is 0.22 meters. So let's go back and plug in our numbers with a number with an SI unit. So this wasn't working here. That was a bad approach to use inconsistent units, the centimeters and the meters. So let's get rid of all that, and we'll put in 2 times 0.22 meters over the acceleration of gravity. And now our meters cancel beautifully. And my calculator is telling me that that is a time of 0.21 seconds. And it is seconds, not seconds squared, because we have the square root here. The square root of a unit squared is that unit.
Made with Doodlecast Pro.